Is it 30 yet?
No.
No. I got told off for starting early yesterday, so better not today. Because they're filming it. What?
No.
Oh, it's not late. Okay, good morning.
Morning.
Have you got, what talks you just been to this morning?
Some horrific ones.
They just sucked all the energy out of you, did they? Okay. Yeah, so we spent a long time in bed this morning. Well, not together, obviously. So we've got a lot more energy.
Stop, move on.
Okay, yeah. So this morning we're going to be talking about simplifying threads. Hands up who writes multi-threaded code. Okay, cool. So if you write multi-threaded code, typically, yeah, if you want to write it so it's really scalable, you have to really think quite hard about what locking strategies you're going to kind of use in terms of how you lock stuff and stuff. The downside is you can do very simple locking, and hopefully your code will be thread safe, but maybe you have scalability issues. You're not doing it, can't tune it enough to get maximum concurrency through it. On the other hand, you could be very loose in terms of your locking strategy, and maybe it works and maybe it doesn't. Okay, occasionally it might go bang and that kind of stuff. But the problem is once you get to that kind of level of complexity in terms of really tuning it, often the readability of your code goes south. Right? Someone looks at your code who's not used to multi-threaded programming and looks at it and says, I can't really see the intent here. This is a code I'd have written if it was single-threaded, nice and simple. This is a multi-threaded one. It's hard to read and hard to maintain. So what we're going to try and do today is we're going to try and talk about how we can write multi-threaded code that's highly concurrent, is optimal for concurrency, but hopefully still simple to read and understand. That's the goal. Okay. So, greater concurrency without complexity, that's what we'd like to achieve. In order to achieve this, I'm not going to write my own locking strategies or anything like that. Hopefully we're going to use stuff that Microsoft has given us even as early as .NET 4. So in .NET 4 they introduced some new things, LazyFT. Who's used LazyFT? Yeah, quite a few people. The most awesome type on the planet when you really get into it in terms of concurrency, but on the surface it's very simple and think, well, is it really that useful? But we'll see, very useful thing indeed. Concurrent collections, so these are things like concurrent dictionary, concurrent bag, concurrent stack, concurrent queue, came out in .NET 4. We'll look at how we can play around with those kind of things. But the last thing we talk about, the new goodness that came out in post 4.5 is immutable collections. Who's using immutable collections? A couple of people. Sounds a bizarre thing. You can have a list that you can't add to. It's really useful, isn't it? You can imagine that. A cube that you can't add to, which is awesome. Okay, so we'll talk about immutable collections, the thing we can do with these collections that are immutable. But the good news about anything that's immutable, when we start talking about multi-threading, if we're working with immutable types, what do we not have to worry about? Locking, right? Because if all we're ever doing is reading, and that's all you can ever do from an immutable type because it can't change, then hopefully we get rid of all our locks. Okay, so there's a good reason about why you might want to use immutable data structures. Okay, so like I just said, really, the moment we start looking at concurrency, start throwing multiple threads at a piece of code, we end up starting to use locking semantics or synchronization stuff. We either go simple, which you don't get much concurrency, or we go complex. And at that point, we start losing readability. The sweet spot is to try and get both. Okay, just filters in code. We don't want to use slides, do we? And we have no code on the screen. That'd be awesome. Start Visual Studio then, that'd be a plan. Okay?
We might have to fill for a while.
We might have to fill for a while, I think. Yeah. Oh, I don't know, it's reasonably
pretty
quick.
fast today.
Yeah, okay, and there's a project there already with inside demos. Yeah. Yeah, that's the one. Simplifying shared state. Okay, yeah, that's good. I guess go full screen. Maybe not like that. Okay, cool. Right, there's a little bit I have to tell you about the code first. It's not too complicated. Okay, we're going to be processing CSV files. You all happy with CSV? Yes, okay. It's even older than XML, right? So you're cool with that, aren't you? Okay. Okay, so CSV file. So we've got this thing called a class called CSV repository, and we give it a directory. Its job in life is, at the moment, is it loads every single CSV file that's inside that directory into memory. Okay. We've then got a for each loop underneath that walks through every single file and saying, I want to take each CSV file, I want to take every row, and I want to map it to an object. Okay. Okay, so that basically that line that says repository.map, I give it the file that I want to load that's already been loaded into the CSV repository object, and then I give it basically a lambda there that says this is what I need you to do in order to convert a CSV row, a comma separated series of values, into an object. So what we're doing is we're basically loading all the CSVs into memory, we're turning them into string arrays effectively, but then actually when we ask them to be mapped, we actually turn them into objects. Okay, everybody happy with that? So just a simple repository. If we scroll up a little bit, the one thing that's a little, when I create the repository, you'll notice there, give it the directory, also give it a function, the strategy that we're going to use for loading. But rather than just open the file with a stream reader, we're incrementing a count. I want to know how many times we've loaded a file. Okay, and we'll see why that's important in a bit. Okay, so I'm just going to run the code and see what happens. Okay, so these are all the CSV files it's loaded. It's loaded them 37 times.
Can you read at the back?
Can you hear him at the back?
I can't really see the C# code.
Sorry?
I can't really see the C# code.
You can't.
There's a big thing in front of it.
I like that. That was good. That was good. Can you see it now?
Yeah, I won't say anything more now.
No, do you want me to put the font up a little bit?
Yeah, please, thank you.
Well, there's a seat here. No, just kidding. You stay there. It's comfy. It's easy exit at the back too, right?
I actually was looking for seats, but can't really see any.
Looking for what?
I was looking for a seat further down, but didn't.
Oh, there's plenty here.
That's too far down.
Okay.
Is that better?
Is that okay now?
Yeah, thank you.
Loud enough? Yeah. Okay. Wow, that is big. Okay. Okay, right. So, if we go and have a look, let's go and have a look at the CSV repository constructor real quick. And inside there, we'll see very quickly, we look at the CSV files line here. Basically, this is the line of code that's building the dictionary. Okay, so when you create instance of the CSV repository, it effectively builds us a dictionary and loads all the data into the dictionary. Yeah, okay. Let's go flick back to main a second. Yeah, that'll be the one. Okay, uncomment the parallel.4. So parallel.4, if you were in my workshop on Monday, you don't know what that does. What does it do? Parallel 4 allows us to execute stuff in parallel, right? So we're basically running that piece of that for each 10 times in 10 different inside a different task. Okay? Yeah. Now, we're then going to print out how many times it's loaded the file. Well, at the moment, we're loading the file as part of the constructor, so we should still see 37 times, even though we've got 10 threads, each asking for the same CSV file. So let's go run the code. 37. 2 more times, just to be sure. It's multi-threaded code, it's hard to test, so we always run our code 3 times, and if it works, check it in. So it works, so there's no big surprise there. But the problem with this is, we could say that, well, yeah, our algorithm's okay, but we're loading all the CSV files up front. Probably what it'd be better to do is to load them on demand. Yeah, so as someone asks for a CSV file, we'll try and load it. Okay, you want to comment on that again? Okay, that's good, let's do that. Let's make it simple. Yeah. So let's go to our code. We're going to assume single-threaded again. So instead of preloading the dictionary here, let's put a null value in there, Rich. So do you want to comment that line out? Yeah, Rich is my code manager. I didn't even say who I was, did I?
No.
I didn't. So my name's Andy. This is Richard. Yeah, we don't sleep together. Okay. So we need to do a list of string array. Yeah, you could call 2 lists on us. Yeah. Yeah. Right. Brilliant. Okay, cool. Okay, let's go scroll down a bit. Okay, so we're going to. So no, not in there. Inside the app. This is the piece of code that we've currently got. Is that simple? Everybody nods because the demo is going to tank otherwise. Okay. That's simple code, isn't it? What are we going to replace it with now? We're not pre-populating the dictionary with the actual data. We pre-populate with the keys, but we haven't pre-populated the data. What are we going to do here? What's this code going to look like? If they're very cooperative today, aren't they? Really? If CSV file square bracket data file, you're in the wrong place. You touched that trackpad again.
I think so.
You did, didn't you?
You rename them.
Yeah. Okay. Yeah. That's equal to null. What are we going to do here? Just load the data. So we say CSV files. Yeah. Not that. Yeah. Equals load data. Data file. Yeah.
To list.
Yeah. All good? Is this going to be? Is this good? Is this going to be okay on a single thread? You reckon? You all happy? Run the code. Has it worked? Oh dear. Okay. Only got the single. We haven't got the multi-threaded yet. You failed. Okay. The reason is collection was modified. What are we doing to the dictionary? We're adding stuff to the dictionary while someone else is iterating through the keys. So while we're doing enumeration and iterating through the keys, we're trying to add to it. So we need to fix that. Just put 2 lists in there. Okay. Is that going to work now? They're worried now. I can tell. It's a trick. Let's go run the code. That's awesome. 3 times. Whoa. 1 more. Excellent. Okay, cool. Right. Now let's introduce multi-threaded. What do you reckon, multi-threaded? How many times are we going to load the file now, you reckon? Is it going to be 37? Is it going to be 370? Is it going to be 500? So run the code.
Just arbitrary numbers.
Any arbitrary number, I'll just keep going for every number. Oh, 54. 59. 56. Okay? So clearly that's not the plan, right? The plan was to only load them 37 times, right? So there's a really easy strategy we can do to fix this. What would be the easiest way to fix this? Put a big ass lock around it, right? Okay? So go and create, oh hey, I know we shouldn't have said it like that. Go and create me a lock.
Some sort of object to lock on you.
Yeah, I think I know what it's going to be called, right? Yeah, I thought it would be. Yeah. Kind of knew where that was going. Okay, so let's go and put the lock statement in around the if block. Let's do it there. This one. Big ass. Lock ass. Kevin does a talk on naming, you know this, don't you? I'm guessing that's not
Do you want a return statement in the log?
Yeah, let's do that. That is definitely a big ass lock statement. Okay, cool. What do you reckon? Is this going to work? Is it going to be thread safe? Yeah. Okay. 37. 2 more times. 37. Also be checking. Okay. So that works. What's wrong with it though? What's wrong with it? It's safe.
Slow.
Slow. Yeah. And why is it slow? Because well, there's also obviously, if one thread comes in here, it then makes the lock. It then says there's no data file here and it tries to load the data file. Yeah? Okay? So that's an issue, right? Because if someone else comes in and said, I'd like to load a completely different data file, can they load it in parallel? No. They have to wait behind it. So we basically took multiple threads and they're going to spend most of their time queuing up one behind each other. That's not very ideal, is it, really? Okay? So what would we prefer to do? What would we prefer to do? Well, we basically say, well, is it okay to load that CSV file at the same time as loading this CSV file? That would be kind of cool. That's what we kind of like to do, right? Okay. But at the moment, we're just using a single object to lock on. We kind of want to lock on each kind of data file. We can't do that because what's that value? Null. Yeah? Trying to lock on null doesn't work. Okay. So we can't do that. Okay. So what do we want to lock on? Well, people say, well, why don't we lock on the key in the dictionary? That's there. Well, we can't lock on that. You can't get to those kind of keys in that way. So what can we lock on? Well, maybe we need to think a little bit outside the box here. Why did we pre-populate the dictionary with null values? Because we didn't want to load the CSV file until someone asked for it. And actually initializing that data associated with the dictionary is costly. It requires I/O. We want to delay it until we actually need it. How about we just put a very, very cheap object in there? Not the actual CSV file, but we'll just put a cheap object in there. Once you put a cheap object in there, we can lock on it, and it's cheap to create. So go to the top of the code, let's go and create this a public class called virtual CSV. And in there, I just want a single, virtual app. Okay. And inside there, let's do a public list of string array. Not in capitals. You can read it at the back though, which is good. Right?
List of string array.
Yeah. Okay. And equal range. Excellent. Okay. Right. And then inside the dictionary now, instead of having a dictionary of list of string array, you were there. Okay. So get rid of that. And we do new virtual CSV. Okay, so we've got cheap objects. Okay, .NET's really quick at creating objects. It's a very, very cheap object now. Okay, yeah, you'll need to go and change the signature, the dictionary. Yeah, awesome. Okay, I'll get rid of that angle bracket. Okay, cool. Okay, so now we're creating this really cheap object, which means down here now, scroll down, scroll down. What can we do? Instead of doing big ass lock here, what can we do instead? We can lock on that. Okay, so let's go and lock on that. Okay, there you go. And then basically we'll say is the rows null. Okay, and then inside here, what do we want to do? We say dot rows. Use that, and then we go and change that bottom line now to dot rows. Okay, all good? Yeah? So now we've got finer grain locking going. Okay? Let's compile it. Let's test it with our sophisticated unit test. 2. All good? You all happy with that? Why does this still suck? You see, all we're ever doing is reading from the dictionary. Once we've loaded that CSV file, all we're ever doing is reading. But every time we go and ask for a particular CSV file, what are we having to do? Obtain a lock. Okay? Does that feel good? Really, what we should be using is an algorithm called double check locking. Was anybody in Alan's talk yesterday on double check locking? No one. Well, that's all right. Good. Yeah, Alan basically said yesterday that double check locking doesn't work in .NET. Doesn't work reliably on Java. As of CLR version 2, there's a strong memory model, and double check locking does work. Okay. Otherwise, there'd be lots of broken code in the runtime and in the framework libraries, which would clearly be broken. So double check locking works like this. You check twice, right? So instead of doing the no, not there. It's not like do if twice, just to be sure.
That's a double check.
Yeah, it is clearly a double check. Absolutely, I can't deny that for a second. Okay. Whoa! Did you just go big there?
Oh, I've got a problem there.
Yeah, I know.
I shouldn't have put this aside.
No, I think you should have either. I don't know what you did. Awesome. Cool. Okay, so this is a more efficient. So we're only obtaining the lock when we have to create the CSV file. If it's already loaded, we don't obtain the lock. Okay, so we minimize the amount of synchronization required. Let's go run it. Fantastic. 2 more times.
It's much faster, I've noticed.
Yeah, I've noticed. The front here, they're very happy now. It's fast. Okay, all good. Now, that's the piece of code we just written. The commented out piece of code at the bottom is what we started with. Which one's simpler? Okay, I think that's a resounding yes. So the bottom line is simple. This is a little bit more complex. It requires you to understand double check locking and understand those kind of semantics. And it's a very simple problem here. What we'd like to do is refactor our code so we basically end up with something that looks like that bottom line and get rid of all that stuff. Okay, that's where we're going. So this is what this talk is really about. It's taking code that's what we historically would have written, and hopefully in a minute write it far simpler. Okay? In order to make it far simpler, we're going to introduce this new type called lazy of T. Okay? So let's go and flick to program.cs for a second. Okay, I'll go and create me an old main. Yeah. I'll go and create me a new main. Yeah. Okay, alright. So I'm going to create me a class called person. Let's do that. And inside the person, let's have two properties, name and age. Excellent. Okay, cool. Inside there, create a new instance of a person. Oh yeah, create constructor, yeah. Oh yeah, yeah. And let's print out created. Excellent. Okay. Inside here, let's say person. Yeah. New person. And initialize it in however way you'd like. Yeah, cool. And then set my age in a kind fashion. Oh, that's nice, isn't it? Okay. All right. then, okay, okay, and then like, can you print out my name and then my age? It's 2 separate lines. Yeah. Awesome. Okay, cool. All right. And before you, yeah, after the age, just put a line that says, I don't know, person initialized. Okay, let's go. What's it going to show us on the screen when we run it? There's no threads here. There's nothing complicated. Okay. It's going to say the constructor runs. Then it's going to say person initialized. Then we're going to print out my name and this fictitious age. Okay. Right, let's go run it. Okay. All good. Okay. Okay. So it creates the object. It turns out there's this type called lazy of t, and lazy of t is all about delaying creation. In other words, I'll create a lazy object, a lazy of person, and it won't actually create the person object at that point. The lazy of t has a property on there called value. Okay, and the first time I ask for the value from the lazy object, at that point it will create the object. In other words, the lazy object's cheap to create. It may be that the thing it's wrapping up is expensive to create, and we only want to create it when someone asks for the value. Okay, so let's go and refactor to that a second. So we've got a lazy person. Yeah, I wish you won't pick my name there, right? Okay, so so we're going to, instead of creating a person here, we're going to do a new lazy of person. Yeah. Yeah, excellent. And so we can't say then lazy person dot name here. We do dot value. Okay. Okay. Yeah. Okay. And then after we create the lazy, leave that person initialized to underneath the lazy. Yeah. Okay. Oh, you messed up, man.
It was so good, then.
They were going to be impressed with your parallel programming. Right? Okay. Yeah, so lazy. Okay, so what are we going to see on the screen this time? We're going to see lazy created, and then after that it should say, if I've said it's true, the first time you access the value, it will create the instance. Okay, once it's created the instance, every time you ask the value, you get back exactly the same instance. So we should only see the constructor run once, even though we're accessing value 4 times. Okay, so good, wasn't it? Okay, so lazy create, person initialized. All good? Yeah? Okay. So that kind of works. But you know what? I can't change my name rich, so let's go and change the constructor now to take a name. And let's make the name read only. Yeah. Cool. Yeah, no, I would say. Okay, so scroll down. Clearly now we can't do that line of code. So let's just comment it out for now. Okay. What is going to happen when we run this? Is it going to compile first of all? Does it compile? It compiles. Is it going to run? No. Well, the thing is, how would it create something? Let's go run it. Boom. The lazy initialized type does not have a public param plus constructor. In other words, lazy of t, as you've seen so far, only works with types that have a public param plus constructor. What technology do you think it's using to create the object? Reflection. Does that rock? In a multi-threaded environment where I'm not trying to get through things through quick, should I be using reflection? Does that feel good? Well, it wouldn't feel good from a performance perspective potentially, but what else it doesn't feel good at is having a lazy object that moves up a type that doesn't have any inputs is generally pretty rare to need that kind of thing. Right? We'd often want to pass in some creation parameters. In this case, we want to pass in my name. Okay? So most of the time, I definitely recommend you do this anyway, is you specify a function. Okay? In order to say, so when lazy of t, for the first time is asked for the value, instead of using reflection now, it evaluates that lambda, okay, to build the object you need. In other words, it's a function factoring, yeah, okay? And now we've basically got Andy being created. Yeah? All happy with that? The really important thing about lazy is it's thread safe. If 2 threads ask for the value, one will be told to wait, while the other one is creating the value. Once the value's been created, yeah, the other thread will share that same value. In other words, that operation, that function could be taking a very long time. It could be loading a CSV file And if someone else asks for that CSV file, they'll get told to, you have to wait. And once that CSV file is loaded, they'll both be sharing that same piece of data. Okay? So based on that, going back to our original piece of code, we can do a simple refactor now. Go to the top. Instead of having a dictionary of virtual CSV, let's go to the top. Yeah, we want to have a lazy of list of string array. Okay? You must love this. Look at all those angle brackets. You like angle brackets. Only we had a t-shirt with it on. Yeah, that'd be cool. Yeah. Okay. So inside here, what do we want to do now? We want to just create an instance of the lazy object and say to the lazy object, if you get asked for your value, this is a CSV file you need to kind of load. Yeah. F.name and then two lists. Okay, cool. Okay, let's scroll down. So remember all that double check locking we had? It's commented out. And the next line. And we'll leave it there for posterity. Okay, let's go and rob that line. That was a simple line. Let's put that at the top. Awesome. And all we've got to do now is change that single line to dot value, and we're done. Okay? Yeah? So we either have all that complexity, or we have that single line. Which one's better? If you get paid per line, clearly the second one. Okay? If you want job security, maybe the second one. But hey, 30 degrees. Okay? That's what we're talking about here. We're not talking about having to use interlock and low-level stuff if we don't have to. We're talking about trying to use these bigger abstractions that Microsoft created for us to make it easier for us to express code, make it easy to read, but at the same time be highly concurrent. Okay? So this kind of works. There's a slight downside with our implementation, right? When we new up the CSV repository, it goes to the file system and does what? It enumerates all the possible CSV files in the directory and pre-builds a dictionary with lazy objects. Which means if later on someone drops in another CSV file, we don't get to see it. Okay? So maybe a better approach would be, well, we don't want to pre-populate the dictionary. When someone asks for a file, we'll say, is it in the dictionary? If it's not in the dictionary, we'll go and look on the file system. If it's on the file system, we'll then load it. In other words, we'll be able to discover new CSV files that arrive. The thing is, we've got away so far using a regular dictionary. And we've got away using a regular dictionary because really all we're ever doing is doing what to the dictionary? Mainly just reading from the dictionary. Okay? If we're going to have multiple threads adding stuff to the dictionary over time, we can't use the regular dictionary object unless we start throwing lots of lock keywords at this. Do we want to use lots of lock keywords? No. Okay. So there's another type that we could use, which is called a concurrent dictionary. Okay? And a concurrent dictionary will obviously allow us to use this across multiple threads. Okay, before you go and do all this refactor, let's go flip to the side. So, okay, let's go. We talked about lazy. Let's go. So this is what we're talking about using now. We're not going to be talking about using the regular collections that we're used to using as regular developers. We'll use ones that are designed for concurrency. Yeah, designed to be accessed across multiple threads at the same time, effectively. Okay. So, and people look at this for the first time, they think, okay, that's cool. Microsoft have grown up and they've realized that the Q class, the stack, and the dictionary are not thread safe, so they've now made them thread safe, and they're exactly the same, they're just thread safe. Well, that's not true. In terms of the APIs have to be built differently for concurrency than they would be for non-concurrent environments. Okay? So this is the example of the regular Q class that's not thread safe. So here it is, a new queue, and we can call q.enqueue. We could then have a thread, okay, that was saying q.count is greater than 0, and then dequeue. Because with the regular Q class, if you try and dequeue and there's nothing there, what happens? They've never tried it. Yeah, it throws an exception, right? Okay, so really the programmer said, well, I don't want to catch an exception and say, oh, oops, there wasn't anything in the queue. I should do the right thing. I should say, is there anything in the queue? If there is, I'll attempt to dequeue. Okay? Now, they could have written a thread-safe implementation of the data structure for the queue object and made sure that only one person at any one time was calling one of the members of the queue class. But that's not going to work, is it? Because they could protect that one thread is only talking to count, and only one thread at any one time could be talking to dequeue or count. Okay? But the problem is, the moment we add a second thread, we have a race condition. 2 threads come in, one says it asks for the can, the other one gets told, oh, someone's already in the queue object, you have to wait. One gets the result of there is 1 item in the queue. The other one now can ask, how many items are in the queue? It gets told 1. They both move forward to dequeue, one succeeds and the other one fails. Really what we need to do is combine the can I dequeue something and dequeue as a single operation. Yeah? In other words, make a far bigger API into less granular effectively. So we'll see that these concurrent data structures have very different APIs than what we have on the traditional ones. So on the concurrent queue, we don't have a method called dequeue, we have try dequeue. Okay? Yeah? On the concurrent dictionary, we have triad, not to be confused with Chinese mafia, okay? But we basically try and add, okay, things to into the dictionary, right? Rather than actually say check and then try and add it. Okay, let's go. Yeah. Okay, cool. Let's go to the code then. Okay. So we're going to refactor this now to use a concurrent dictionary. Okay. Cool. And then we clearly down here we want to create this to a concurrent dictionary. Excellent. Okay, cool. All right. Now scroll down a bit. Okay. Okay. So this is what the code we had before. Now clearly that line isn't going to work here. So what do we want to do now? Because it may be that the file you've asked for is not in the dictionary. So what should we do here? We do this kind of code. Look for it if it's in the dictionary. If it's not in the dictionary, go and add it to the dictionary. Would this be good? No, it wouldn't. Yeah. You shouldn't ever even do this on a regular dictionary, should you? You should never say, does the dictionary contain this key? If not, I can add it. Okay, why should you never do that? Or put it this way, let me put it this way. What about this one? Should you ask the question, is it in the dictionary? Oh, yes, it is. Now go and get it. Is that a good question to ask? If you went to a warehouse and you went to the guy in the warehouse and said, do you have this widget? And off he went, down a few flights of stairs, round to the back room, says, yo, we've got it. He comes all the way back and says, yes. And then you say, now go and get it for me. What would he like to do to you? And that's the same thing with a dictionary, right? And most people do this all the time, right? Okay. So we don't want to be doing this. Okay. So let's come in here. Don't want to do this. Don't want to do this. What are you doing? You're determined to go and write this code, aren't you? Local data store slot. We're not doing anything with that. See, Richard's my code monkey. He's not meant to have any free will. Okay. Now, I don't know if you've noticed today, he's already getting well ahead of himself. All right. Let's go back to where we were back at the beginning of this method. Scroll to the left. Excellent. Good. Right. You're deliberately making this hard for me today, aren't you? I can tell. I thought we were getting a rhythm, you know? Okay, just comment it out. Right, okay, go up to the top. Okay. What do we need to do here? Okay. What we need to do is, we need to basically say, if it's not in the dictionary, we need to add something. If it is in the dictionary, we need to use the values in the dictionary. Yeah. It turns out there's a single operation to do that. Okay. We can call an operation on the dictionary called get or add. Okay. That's on the concurrent dictionary, it's an atomic operation. I either want the values in the dictionary if it's in there, if it's not, this is the value I want you to put in. And as far as the dictionary is concerned, this is an atomic operation. Okay? Now, obviously what we're doing here is we haven't got a dictionary of actually containing the CSV files, we've got a dictionary of the lazy objects. That's convenient because lazy objects are cheap to create. So we can create a lazy object every single time we come into here, representing the CSV file we're asking for. And all we need to do here is say CSV file get or add. We'll either add our lazy object, yeah, if it's not already in the dictionary. If it is already in the dictionary, we get back the previous lazy object that was already created and put in the dictionary. Okay? And then effectively just use that item.value to go and get the value. Okay? Yeah? So now we've got a situation where we've got a dictionary that is not pre-populated. As we ask for a CSV file the first time, we'll go and add it to the dictionary and load the data. If at the same time someone else comes in and says, I too want the same file, and it's in the progress of being loaded, they get told to wait. Okay? It's still pretty very, very simple code compared to what we'd have to write it if we go and use double check locking and various other. Oh, if it even compiles. Just a semicolon. Bracket it.
Simple for anything.
Cool. Brilliant. Why did it fail?
Like 3 times.
Told you it was a smash zone. Okay. I know why. Go up to the top. It's all right. I know why. I just realised. Okay. CSV-files.keys.toList. That's the list of files that are in the dictionary. You don't want to do that anymore. Get rid of that. And the toList. And the keys, because there's no keys in it to start with, right? So we just need to new up a directory info. Basically, copy that bit of code you got above. There you go. Okay, and then, yeah. Yeah, enter. And then you want dot select. FI goes to. Offset that. Select. Okay. FI goes to. Okay, semicolon. Yeah, cool. Go and compile, run it, ship it. 37. Again, 37. Awesome. We're happy with that? All good? Okay? So you see we've got a dictionary now that populates itself on demand across multiple threads and loads things in a lazy fashion. And the code, I think, is pretty damn simple. Okay? Okay, let's go. Should we do slides? Yes, do slides. How's it for time? Okay. We've got 50 minutes, yeah? So we looked at concurrent dictionary. Let's go to another project a second. Let's have a look at that. So if you create a regular list, yeah, and then you populate it with 10,000 items, and you know you're going to populate with 10,000 items, what should you do? When you create the list object, you should say it's going to contain 10,000 items. Why do you need to tell the list class that's how many items it's going to be? Well, how does the list can grow, right? Yeah, and if you create a list object by default, how many items are in the list? Potentially 12. Yeah, and if you once you go to add the 13th item, what does it do?
Double it.
Doubles it, but how does it double it? It has to create another array which contains 24 items and copy those 12 into the new one. And when you add the 25th, what does it do? Doubles it and copies everything again. Okay, so if you know you're going to have 10,000 items, you should really tell the list class, create me one big ass array of 10,000 items, and we'll just do the initialization once, not many, many, many times. Okay? The same is kind of true for a concurrent dictionary, right? So here we've got a concurrent dictionary which is going to populate with how many items? I've only had C#6, right? The top feature of C#6 is this, right? You must have seen it all. Yeah, you can put spaces in numbers. Is that a good feature? They're all loving it, aren't they? They're just sucking it up. Okay. Okay, let's go delete that. So how many was that?
10 million.
10 million. Okay. So we use the parallel of 4. We're going to have multiple threads that are going to cooperate to add all 10 million items in. Okay? So let's go and run the code. So we're brilliant. Dictionary's never got that exciting, right? Yeah, cool. Let's press enter. Cool. Right. Yeah, Visual Studio's not designed for 10, 24, 7, 6, 8. Funny that, isn't it? Okay. So how long is it taking to populate the dictionary? Got multiple threads working on this, trying to do it at the same time? 10.6 seconds. Okay. And that's because we haven't given the dictionary any hints or tips about how big it could be. Okay. So it turns out there's 2 parameters we can pass in here. How big it's going to be, that's a similar thing we do with a list. But we can also say how many threads do we ever expect to be accessing this at the same time. This allows it to allocate sufficient locks in order so we don't get much contention. Okay. So yeah, you can do process count if you want. Yeah, fine, comma, and then it's how many items, number of values. Oh, you got that the right way around. Wow. Okay.
10 million threads.
10 million threads. You don't get an exception to that, would you? Okay, that's cool. Okay, 10 seconds we've got to beat. 4.1. Okay. If you use a concurrent dictionary and you have a reasonably large number of things and you're going to populate it, across multiple threads, you definitely want to pre-initialize it. Okay, that's a big speed improvement. Okay, let's go slides a sec quick. Okay, so there is a concurrent queue, there is a concurrent dictionary, there is a concurrent stack. There's one obvious one that's missing, and that's a concurrent list. And you must admit, list. Do you all use list every day? I mean, list appears a lot in code, right? I mean, if you scan your code, you probably have used a list a lot. But there is no concurrent list. There is a concurrent bag. What's the difference between a bag and a list? Okay, one's for saying what you want to buy, and one's for putting your shopping in, right? What's the difference between a bag and a list?
A bag of tea.
Bag of tea. Have some fun with this, couldn't we? We could do a t-shirt for you. Yeah, you like that? Ooh, okay. What's the difference between a list and a bag? You do computer science, you must know this. A list preserves order, a bag doesn't. If I put 3 items into a bag and then take them out, I have no idea the order they're going to come out. Okay. And it turns out, you think, well, why did they ever not build a list? Well, if you know a little bit about the history behind these data structures, it kind of comes out a little bit in the fact that these were not written for, oh, let's write these data structures because they'd be useful. When they built what the Parallel framework extensions like Parallel.4, Parallel.4 each, they built these data structures to enable them to build Parallel.4 and Parallel.4 each. And then they said, you know what, we built them, we might as well make them available. They had no reason to have a concurrent list. So a lot of people go, you know what, we've got a bag though. You know, if I don't care about order, maybe a bag is my thing of choice. Okay? So I've got multiple threads that need to record things in a single place. Maybe I should use a concurrent bag and I'll just throw things in, and I'll use another thread later on to go and pull all the items out. If you do this, you will have misunderstood what its intent is. And in fact, in some ways, it's kind of nasty they just call it a concurrent bag, really. Do you feel in an artistic mode today? Okay. If you've got a smartphone camera, okay, at the end, Richard often signs the pictures. Okay, they go for loads on eBay. If you grab it once the signature's on, the value doubles, isn't it? Is that right? Yeah.
Pretty much. Yeah.
So Richard's going to draw you a piece of code now. Yeah, this little symbol here is a thread. Okay, and we've got 3 threads of execution. Okay, these 3 threads effectively are going to share a common bag. It's a concurrent bag. Okay, so draw me a bag, Rich, in a rectangular form. Okay, awesome. And the idea would be that, don't draw anything yet, the idea would be that these threads would be adding stuff to the bag, okay, at the same time. The thing is, if they're constantly adding to the bag at the same time, what kind of thing will we have to worry about? Thread safety, synchronisation, you need to make sure only one person perhaps adds to the bag at the same time. But that's not very concurrent. And the idea, this is a concurrent bag. We want threads to be free running, adding to lots of them, adding to the bag at the same time. So we need some way to reduce contention. And the easiest way to reduce contention is to say that that big bag is actually made up of a series of little bags. So each thread actually has its own local bag. And if the only thing adding to its own private local bag most of the time is going to be itself, then there's no contention. So everybody, when they do an add, will by default always add to their local bag. Okay? Yeah? Not so good today. Okay. So we now have contention. But you can imagine now, if all I'm doing is add, this is good. And there's another operation you can do on a bag, which is take. Give me the next one, take the next thing out. And by default, again, each thread will always take from its local bag first, because that's the place of least resistance. There shouldn't be many other threads touching this ideally. Okay? However, if you say to one thread, give me everything in the bag, take, it will go to its local bag. But when it runs out of items, what's it got to do? It's got to steal stuff from other people's bags. Okay? Yeah. So eventually this one will take its single item it added, and then after that it will steal. It will then steal. Why is it upset what you found in that bag?
It's a sad operation.
It's a sad operation. Okay. It basically has to go to someone else's bag and steal the stuff. Okay? Now at that point, we've got contention. That thread could be adding stuff, while that's just trying to take stuff away. So from a multi-thread perspective, it's not ideal. Okay? So the concurrent bag is really designed for scenarios where most of the time, all you're ever doing is adding and removing from your own local bag. Okay, it's not really for lots of threads add to the bags and then have another single thread that's responsible for taking everything out of the bag because you're going to have to touch all those other bags. So it's not ideal. If that's what you want, you're better off using a list class and a lock. So what's it designed for then? Well, it's really designed for certain types of problems, really. Mainly for this idea of almost like divide and conquer or basically taking a piece of work and subdividing it. So can you imagine this? If you wanted to walk a directory structure in Power and process the files, we might have a thread that goes to a directory, and in that directory will be some files to process. There'll then also be some subdirectories. Each of those subdirectories will have to be visited. We'd like other threads to visit those. Yeah? And it may be that once you're inside that subdirectory, there'll be further subdirectories, etc., etc. Well, it turns out we can use a bag for this. Yeah? We can basically have a bag which perhaps contains an initial directory. Yeah? Yeah? And inside, when you open that, take that item out, you see the series of other subdirectories, and you add those subdirectories to the bag. Other threads are then taking stuff from the bag. They'll take that first subdirectory. They will then look at the files in that subdirectory, but they'll also look at all the subdirectories in that subdirectory and add them to its local bag. In other words, they'll create work for themselves. But if another thread runs out of work for itself, it can still work from someone else's bag. So it gives us a way of distributing work without having to worry about writing some load balancing algorithm. Okay? So we've got some code here called parallel tree walk. And effectively, like I said, the goal of this algorithm, I'm not going to go through the algorithm particularly in detail, but the thing is, the algorithm is going to be constant. What we're going to vary is the data structure that we're going to use to remember where the directories are that we need to visit. Okay? Okay, so the way that's done is we've got this thing called a list node heap adapter. That is currently using a regular .NET list, yeah, and it's using an add operation, but before it touches the list, it needs to remember to lock it. It's not thread safe. Similarly, when we want to take something out, again, we'll do a lock. Okay? So let's go and run the code. Now the code runs twice because touching the file system, there's caching issues and stuff. So just to make it 100% fair. Okay, so the first run took 3.7, the second one took 2.5. Okay, so 2.5 is what we're going to try and beat. Okay, so let's go and recreate another class, Rich. And this class is going to be called the bag node heap adapter T. Adapter T, that's fine. Okay. I node heap. Okay. I need to implement I node of heap. Okay, and let's implement the interface. Yeah, that's good. Okay, and create me now, instead of using a list now, let's create me a bag and I tree node of T. Or concurrent bag even, yeah, so that'll be good. I tree node of T. And new it up. Excellent. Okay, so the add operation, we need to add something to the bag. Okay, so we say bag dot add, and then we're going to try and add the node. Okay, and then this is a real simple adapter. So all you're going to do is basically wire it through. So just say return bag dot try take. So if there's nothing in the bag, it's going to return false. If there is something in the bag, it's going to provide an add parameter. Okay, so pretty simple. No locks involved because it's a concurrent bag. Okay, let's go and flick to program.cs. Let's flick it over. Okay, so let's comment out. So no, keep that one. Okay, yeah, do that one. Sure. Okay, let's move one of those up. Okay, that's good. Yeah. Okay. Let's go and compile it, run it, ship it. Yeah, 0.5 seconds. Okay? Was that a hard bit of code to write? Was it really, was it? Yeah? So that's taking use of a bag. But like I said, it really depends on the algorithm we're trying to build. Here we're trying to basically say, we have a piece of work that can be subdivided and subdivided and subdivided. We want many threads to work on it. Yeah? Each one taking responsibility for subdividing it a little bit further and a little bit further. Okay? And if they run out of work, we don't want those threads to be idle. We want to be burning all our tools. We want to be able to steal work from someone else. Okay? And all we have to do is use a bag, and it basically gives us exactly that kind of behavior. Okay? All good? Okay, cool. Right, okay, let's go. So, there's kind of a clue in the title here. They are concurrent collections. They don't block. Okay? So in other words, they're designed for concurrency. So they're always meant to return like that. They never block. I mean, is that an issue though? Let's go and write a quick bit of code real quick. Let's go and build a standard kind of pattern here, producer consumer. You will have your producer consumer pattern? Yeah? So go and create me a concurrent queue of integers. Yeah, cool. Excellent. Can we now go and spin up for me 4 tasks? Yeah, that's a good magic number. Okay, task.run. Yeah, and goes to consumer and passing the queue. Yeah, and then generating that. So we're going to spin off, we're going to create a concurrent queue. We're going to create 4 consumers. Their job is to consume items off the queue. And then we're going to build a producer that will basically put items into the queue for us. Okay. So we call the end of that line. Task.run. Okay, cool. Inside the consumer, let's do a while true. Yeah, cool. Cool. Okay, and inside there, what do we want to do? We want to take an item out of the queue. How do we get things out of the queue? DQ. Try DQ. Yeah, so we have to give try DQ. So here we'll say q dot try DQ. Yeah, out val. Okay, if that returns true, then we're going to print out the value and the task ID. Let's do that. Okay, so we're going to basically try and take it out of the queue, print out the task ID. We're not in VB now. Okay. Task ID, and then sleep for the value. Yeah, and then print, and then say ready again. Okay? Alright, all good. Okay, now let's go and write a loop. Yeah. And say, yeah, while true. Yeah. And let's just do console.readline if you want. Oh yeah, true, if you want. Put true in there. Yeah, cool, semicolon. Yeah. Okay, and then after that, I want you just to generate me a random number and add it to the queue. Be random? Yeah, cool. And it adds the queue. Thank you. Yeah, I know. Okay, and then R&D.next. Oh, we'll get hash code, that will work.
Give us a random number.
Yeah.
Once.
Well, once. Okay. Let's say 2,000 to 5,000. Okay, cool. Okay, cool. What do you reckon? Compile, ready, ship it, you reckon? Should work? Okay. Press enter. Enter. 3 times. Enter again. Keep pressing enter. Okay, so we've got 4. We say, if you press enter lots and lots of times, stuff's going into the queue. As the tasks become available, yeah, in terms of their finished processing the previous piece of work, they'll pick the next thing off the queue. Yeah? All good? Good code? Ship it? Is it getting warm up there?
Very good.
It's getting warm, isn't it? Okay. They're all ready, they're all waiting for work. Let's go look at Task Manager. 50% CPU. Okay. Not very green, is it? Really? I mean, why is it doing that? Go look at the code for the consumer. What are the consumers doing? Try DQ. There's nothing in the queue. What do they do again? Try DQ. There's nothing in the queue. What do they do again? Try DQ. Okay. A bit like kids when you take them on holiday, isn't it? Are we nearly there yet? Okay. Eventually, you know. What do you need to do to the kids if they keep saying that to you? And you don't want to get arrested. Go to sleep. Okay. I mean, basically, we don't want that to be concurrent at this point. We want it to be blocking, really. Okay. So, how do we solve that? Well, the concurrent queues, that's what they are. There's nothing there, they tell you straight away, they're highly concurrent. It turns out there's a type called a blocking collection, and a blocking collection will basically allow you to wrap any of the other concurrent collections to give them blocking semantics. In other words, when you ask for a value and there's nothing there, it says, right, I'll go to sleep. When someone adds a value to the collection, it will wake you up and allow you to get given the value. Okay? So, we're creating instances of a blocking collection. We're passing in there a new concurrent queue. You can pass in a concurrent stack, a concurrent dictionary, any of the concurrent types. They all implement a standard interface that gives you that behavior. If you don't specify anything on a blocking collection, you'll get the underlying storage will be a queue. Okay, so we don't have to do it here, but we've done it explicitly. Okay. What are you doing?
I'm just preserve the code that we have.
Are you trying to preserve the code? Okay, so the blocking collection will wrap up any arbitrary collection, which means it doesn't have things like DQ on there or NQ and that kind of stuff, because it could be a stack, it could be a dictionary. So it just has these two things, add and take. And then the underlying collection, whether it be a stack or dictionary, will do the appropriate thing. Okay? So if it's a stack, it'll give you a FIFO behavior, sorry, a LIFO behavior. If it's a queue, it'll give you a FIFO behavior. Okay? So inside here now, Rich just done q.take. Q.take will block. If there's nothing there, the thread will go to sleep and it won't be burning CPU. Okay. So, all good? Let's go run it. Okay, it's good. Yeah, so it's burning away. What's the CPU doing? Yeah. We'll write down the bottom again. Okay, so this is a blocking collection. Okay. Obviously, once we have things like a blocking collection, we need to have some idea here of ability to basically say, I want to shut everything down when it's finished. That's one thing. The other thing is, as well, this idea of using take here feels kind of a bit horrible. Instead of doing take here with a blocking collection, we can replace this actually with a for each. Okay? So the same way you can do a for each over a list, we can do a for each over a blocking collection. Now, we can be careful here. The blocking collection does implement IEnumerable. But if you do a for each over the blocking collection, it will give you all the items in the collection and it won't be taking them out. If you're trying to go over the collection consuming items, then you need to call a method called getConsumingEnumerable. And that will give you an IEnumerable object that when you do move next, it will take the item out of the collection. Okay? So you say q.getConsumingEnumerable. If there's nothing in the collection, it will block. Okay? All right, so this is a little bit neater now. So can run it quickly. Okay. Enter the area. Yeah, so it's got the same kind of behavior, CPU's doing the right thing. Obviously, at some point, we might decide, okay, there's no more items going to get produced, we need to stop the application. Now, we can either stop the application at that point, irrespective of how many items are in the queue or whether we're processing stuff, or we could do the polite way, the British way, okay? Yeah. We're just going to say, do you say politely to the consumers, we're done, okay? And when you're done, we're all done, okay? So, let's just do a quick check in there. I can do that. I'll just do an if you want. Why don't you say bool quit? Well, not there, outside.
Or here.
Yeah, quit equals false. Yeah, why not quit? Yeah, and then quit equals. Sorry, yeah. Yeah, quit equals that. Dot key, double equals, console key, on a queue. Well, that's clear, isn't it? Key not found exception. That was a good one, wasn't it, really? That's well done, that was. That's a good bit of practice, that. Okay, alright. And then, yeah, okay, let's leave it at that. It's not ideal, but okay. Right. If not, quit. Oh, you can do it that way. Okay, fine. I'll do cleaning that. Okay. Okay. Else that. Yeah. If we don't put that else there, we get an exception because we've basically said here, if you press quit, it's going to tell the queue complete adding. Yeah. If you try and add to the queue after you told it complete adding, you'll say an exception because you said we're complete. Yeah. Okay. And then after that, after that while loop, say print all done in terms of producer all done. And obviously what do we want to do now? We want to wait for all the consumers. Yeah, okay. We're going to do that. We're going to do it, okay, do it that way. Task we put in there. Yeah, and then just add the task to this. Cool. And then right on the bottom, we're just going to say after that, task dot when all. No, wait all, that'd be bad. When that wait all, task dot to run. Excellent. Yeah. Let's go to consumer. So what will happen now is, because we're using get consuming enumerable, if there's nothing in the collection, it will block, unless someone's called complete adding. If they call complete adding, it will come out of the for each loop, because it knows there's no point waiting anymore. Let's come on, okay? Okay, let's go and press ruler. Okay, you can press Q now. So the producer's done. Okay, so we're out there now, we're just waiting for all those tasks to finish. Yeah, they keep how many keys did you press?
No idea.
You have no idea. Okay. Yeah, all the tasks that are completed, 1, 2, 3, and 4, and then, 4, 3, 2, 1, then it says all done. Yeah, all good? That's a blocking collection. Okay, so it's thread safe, but it gives us blocking semantics, so we don't burn CPU spinning on stuff. Okay. So the final thing we're going to look at is this thing called immutability. All right. So immutable, if we write multi-threaded code, so that all we're ever doing is reading from stuff, we don't have to worry about locks. This is a good place to be. Okay. So that's what we're going to play with. We're going to build up a bit of an example first, and then we're going to flip to using Microsoft's immutable collection. So let's go to some code. Okay. So here we've got a simulation of a bank. Okay, and the first thing we do is we basically say how much money is inside the bank. So that's that first bit of code there saying total money in the bank, and it goes and sums up that value for us. Once it's done that, I've then got a piece of code that's down below that while loop that's just randomly moving money around in the bank. So it'll take £10 from that account and add £10 to another account, which should mean all the time the same amount of money is in the bank. Yeah. I reckon there should be a bank account like this, or a bank like this, do you think? You could put £100 in on Monday, and on Friday, yeah, it's moved the money around to the account. You might end up with more than 100, or you could end up with less. Google could do an I'm feeling lucky bank. You don't think so? That would be awesome, wouldn't it? I think we should do that. That's a good start. But what we want to do is we want to verify that throughout the lifetime of the bank, the right amount of money is in the bank. So we've got two threads. We've got a second thread we're going to kick off here, which is task.run, which is going to be constantly in a while loop, adding up how much money is in the bank. And the way we're modeling the bank is just an array of accounts. Okay, so account 0, going right through to account 1,000,000, and each cell in the array has the amount of money. And all we're going to do is periodically, or constantly in a tight loop, just sum all the cells inside the array. But at the same time, people are moving money around. Yeah? So you might be going through the audit doing this, while someone's moving money from down here to up here. Which obviously means if there's no thread safety in here, we're going to end up with some very strange values in the bank. Okay? So, inside here we've just got if the total amount of money in the bank on that background thread is the same as what we started with, we print a dot. If it's not the same amount of money, we print an exclamation mark. Okay? You got that in the while loop? No. So that would not be a very good demo. Okay, so let's go and run the code. So, is life looking good in the bank?
Occasionally.
Occasionally we see a dot, but most of the time we see an exclamation mark, okay, which is not good. Okay. What we're going to do over time now is we're going to refactor that piece of code, but the ultimate goal is to see what? Dots. If you see dots on the screen, life is good, isn't it? Okay. Yeah, it's either busy doing something or formatting the hard drive, but either way, you're really happy because there's dots going across the screen. That's what we're going to do. So let's go and have a look at the code inside the bank. So here's the bank. It's really simple code, all right? So here's the bank. It's got a list of accounts. That property called accounts, that's the thing we're asking the bank for. So sum that, okay, every time. And then we've got some code down here, transfer funds. This is the piece of code where we're actually moving money around inside the bank. Okay? There's not a single lock statement here. It's completely non-thread safe. Hence all the dots and exclamation marks. Okay? So what kind of things could we do here to make it thread safe? What about this then? What if we put on the end of return accounts? What if we did two lists here? We'd take a snapshot, wouldn't we? Would that be good? Well, let's try it, Rich. Is that better? No, not very bad. Okay. Well, clearly we're taking a snapshot, but at the same time we're moving money around. Perhaps you should throw a lock in here. What do you reckon? A lock would be good? Let's create a lock. I'm not going to say the name of the lock, because it's just lock accounts. Yeah. Okay. And then we'll put a lock around the transfer funds. Is this going to work? Hands up, you think it's going to work? 1, 2, 3, 4, 5. Who thinks it doesn't work? Okay, there's more than 5 people in the room. Just for the camera, okay? Otherwise Nick won't pay us, right? Yeah? So this clearly doesn't work, okay? Why doesn't it work? Well, what's inside the list, Rich? It's a list of accounts. When we call two lists on that list itself, it creates a new list. It's a copy, is it? What type of copy? Shallow copy. Yeah? All we're doing is copying references to this object. Those objects are still can change states. Yeah? So we've got a list that points to all the accounts. We've taken a copy that points to exactly the same accounts. This would only work if we were adding and removing accounts. Yeah? Okay? So what type of copy would you do? We could call the deep copy method. Yeah? Yeah? But there's no deep copy method.
You create an extension method.
We could create an extension method called deep copy. Yes, we could do. So let's go and create a deep copy. Yeah, let's go do that. Let's see if this fixes it right. So we need to do a select here. Yeah. And say, I don't know, A goes to new account. Yeah, awesome. ID and then balance. Yeah. This is an awesome bank account because it allows you just to set your balance to some arbitrary value. You'd like that, would you? It'd be awesome, wouldn't it, if you could do that with a bank account. Yeah. Okay. Okay, just two lists at the end. Was it 2 lists? Yeah. We need two lists at the end, otherwise we're not making a copy. Okay.
So I count, which is what it says.
What? It's what? Should be okay. Why is it whinging?
Does it come from the time?
Well, it should be able to. We did this the other day.
You got curly brace rather, so you got straight brace. No, maybe not.
No, it's done. You got a semicolon? No, you give it a semicolon. You need a return statement there if you put a semicolon in there and braces. Yeah. Okay, right. Now I can part. Now I could infer the type. Right, but for other reasons. So we run the code. What do you reckon? It's going to work? Dots.
Our work is done.
It's done. We're done, aren't we? Yeah. Well, 20 minutes to spare. This is awesome. Is this good? Slow. The dots weren't very fast, were they, compared to exclamation marks? Yeah. Okay. Which is weird because it's less to print, right? Okay. So, why is it so bad? Because we're copying the entire list. Is that the right thing to do? Do we want to copy the entire? All we're trying to do is read from the list. But in order to read from this, we've got to take an entire snapshot. Seems like it's the wrong place.
Well, we're cloning the entire bank and we don't want to look at the account.
Yeah, that's it. Is that a good idea? Cloning the entire safe, I guess. You know. Okay, so we're cloning time. We don't want to do that. Where's the right time to do the cloning? It's not in the reading. It's in the writing. Because the only thing we need to clone in the writing is the accounts that we're actually changing. Okay, so maybe it's the right thing to do is to clone it, but we're doing it in the wrong place. We're doing it in the reading as opposed to the writing, because the writing is only changing 2 accounts. We're doing everything in the reading because we have no idea what's going on in the writing, so we have to clone everything. Yeah. So let's comment that code out you've got in there, including the lock.
Yeah, just want to return the accounts, good.
And just return the accounts. Yeah. Okay. Awesome. Now we just need to change the transfer funds method. Okay. So since we've only got one thread, yeah, that's updating here. Okay. Yeah, we don't need the lock key. So let's get rid of the lock. Okay. So what do we want to do here? We want to create a new list, Rich. So let's go and create a new list of accounts. So let's do a shallow copy first. So we'll shallow copy the bank. Okay. Yeah. Okay, so that's a shallow copy of the bank. Now we need to basically create 2 new accounts to represent the 2 new accounts that we're using. Right? So that's new source equals, yeah. Again, that's the source count ID. Yeah. And then set the balance to that to be equal to whatever it was before. Yeah. So square bracket, source account ID. Yeah. Dot balance. Take away amount. Excellent. Cool. Let's copy and paste it. Let's do the opposite. So we make a shallow copy of everything, but then we actually only make a deep copy of the things we are changing. Okay, so just do the things that need to be changed. Yeah. Okay. So let's check out the best account ID. Okay, cool. Okay, and then the final thing we need to do, yeah, is let's get rid of those 2 lines. We don't need those 2 lines anymore. We just need to say new account square bracket source account ID is the new source, destination is the new dest, and then the final thing we need to do is just flip over where the active set of accounts are. Okay, so previously we were pointing to accounts, yeah, and we're just going to change that to this new accounts. Yeah, and that's new dest. And let's do accounts equals. Excellent. Cool. Okay, so now we're only doing the deep copy of the thing that matters. Let's go and run it. What have we got? Dots, you all happy? Oh, you believe that, don't you? Oh, you should have. Is this good? It's better, but what's still bad about it? We're still doing a full shallow copy of the list. You know, and that just feels wrong, right? That we keep copying the list every single time. So Microsoft have come up with this thing called immutable collections, where they try and optimize the memory. So you can have a copy of the list in the new state, but it shares as much as it can of the previous list. And the reason you can get away with that is because if you know the previous list is immutable, you can share stuff because you know it can't change. Okay? So let's go to a real quick example first. So I'm going to create me a regular list, a list of bits. Okay, and this is the audience participation part where you can't say anything wrong. Okay, so what are we going to do here? You create a list. Give me some numbers. 42. Numbers dot add 42.
They could get it wrong.
Yeah, they could get it wrong. That's true. Any other number?
8.
8. Why 8?
You want audience participation, so I can't start questioning the numbers.
Just curious, right? Any other numbers?
F2.
Sorry?
F2.
F2.
X.
Oh, okay, you'll do hex. Okay. No, it was a 0x in front of it. Okay. Okay. Any other numbers?
64.
64. Magic number, that is. Yeah. Any others?
20.
Sorry?
20.
20. Is that good for you? Yeah. Any others? Just put some in, Rich. They're not getting this, are they? Okay. 3, 4, 5.
1, 2, 3.
1, 2, 3. Okay, cool. And then quit 4 each on that. And that's good. Okay. Okay, if you run the code, what's going to show us on the screen? Because this process is this as a hex, it's going to be a little number. Okay, there you go. Yeah? Okay, all happy with that? Okay, so let's now use, while we use a regular list now, Rich, let's use an immutable list. Okay. But this is a NuGet package you have to download from Microsoft. We've already got it here installed. But so let's just comment that line out. Okay. Yeah. And the first thing we're just trying to do here is kind of new up an immutable list. There is no new on an immutable list. And the reason that is that when you new a new list up with nothing in it, what's the state? Empty. If it's immutable, it can't change. So there's no point in newing one up. Maybe it's already got one. If every time you want a new list, we'll just share the same empty list. Yeah? In the same way that we share strings in applications, we're going to share an empty list. Okay, so we've got an empty list. And then we can just call numbers. Does it compile rich? Also. Let's go run it. It's empty. Because it's immutable. You can add stuff, but it's immutable. So nothing's going in. So what do you think it's doing? It's actually, when you call numbers.add, it actually doesn't return void, it returns what? An immutable list that now contains what? 42. Okay? And when you call numbers.add on that list that contains 42, and you're trying to add 8, it actually turns you a new list now that contains 42 and 8. In your refactoring mode. No. You need to avoid numbers in front of the first one. Oh no, you don't know. That's cool, isn't it? Will that freak people out, you think? I think it just freaks me out. Okay. So we've got an immutable list, and then we just basically add 42, add 8, etc., etc., etc. Yeah. Every single one after those add operations is returning us a new immutable list. Okay. Let's go and run it. Cool. And like I said, the implementation could be that every time it's making a complete copy of the list. If it did that, that would suck. Okay? And we'll talk about the data structure in a minute. It is going to be preserving as much memory as it possibly can. Because when it adds 8 to the previous list of 42, it knows that can't change. It's immutable. Okay? And based on that, we can share data as much as we can. Okay? So we're not making huge copies every time. Okay? So Microsoft will give us this immutable list. So we should hopefully be able to go and create the immutable bank.
Always you have to initialize it empty.
Yes.
The first one is empty and then
and then add. I think you can.
You pass it a 9 numeral.
Yeah, you can pass in a 9 numeral as well. Yeah. So if you know an initial state to be that first bit, rather than keep going to create those intermediate.
There's no default constructor which creates an empty.
Okay. So we need to go and create the immutable bank, but there's a kind of an issue here that I can go and create an immutable list of accounts. But Microsoft or most computer science people say that's wrong, because you've got to have a look at the account class first. Or maybe not. Okay, let's go look at the account class, not the I account, the account. You see, if we decided to put account classes inside an immutable list, is it really going to be an immutable list? No, because the balance can vary. Yeah? For something to be an immutable list, really, the list is immutable and its content is immutable. In other words, if you iterate over it, you always get the same data in exactly the same state, effectively. Okay? So this really isn't a candidate for an immutable list. We really need to create a new class called an immutable account. Okay? And there's a kind of a standard way in which you build immutable data types. So immutable account is a kind of I account. Okay. Unfortunately for us, the interface I account is completely immutable because it only has get operations. Okay. So when we create that, we need to pass in the ID for the account and the balance. Yeah. And we need to associate those things with the properties. Yeah. 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 And balance. Okay, so then it's going to be private used. Yeah. You don't want lunch, right? Okay. Okay, cool. So this is an immutable account, yeah? Because once you create the account object, you can't change it. But clearly, a bank that had accounts that couldn't change, it was really good if you wanted to, well, you don't need your money, but other than that, it's not good. So what we need to have is some methods to not change the state of the object, but to create a new object that gets produced when you try and do a state change. So we're going to have a method called with credit, which is going to return a new immutable account. Okay. So you see this kind of pattern where instead of having methods like credit and debit, you have a method with credit, with debit. And the idea is then the with credit method would return you a new account that's in that new state. Okay? Yeah. Okay. You're going to do copy and paste, or you're going to do something more clever than that?
More clever.
More clever. With debit, with credit. Yeah, all happy with that? Okay. Okay. So now we've got an immutable account, which is good. Okay. So going back to, we're going to go and create our immutable bank now. So in there, can you go and create an immutable list of immutable account? So now it's a pure immutable list. The data is immutable inside the list, and the list is immutable. Okay. Yeah. Immutable accounts. Also accounts. Yeah. Equals. Yeah. Immutable list.
Is that right? Mutable enough.
No, they're not. Dot out. Okay? Okay, and inside the add method, what do we do inside here? What does this line of code look like? Do we just say accounts.add? What do we have to write? Accounts equals accounts.add. Yeah, otherwise you'll just be basically throwing it away. Yeah, and then we're going to say new, and then I think let's just do accounts.account. Yeah, let's give it the ID, comma, and short. Okay? Awesome. What does the accounts method need to return? Well, it could just return the accounts. They're immutable. Hopefully happy to be sharing that across multiple threads. Awesome. And then transfer funds. What does that need to do? Well, we need to basically build a new immutable list. And like I said, previously what we did that here, but we take a whole copy of the list structure and then there's a decopy of the elements. Okay. Here we're going to do something like this. No, just do. You'll do like that?
Doesn't it? It doesn't. I have no free will.
Yeah, right. Okay. So that's what we say here. Accounts equals. Okay. And the next line, accounts dot set item. Okay. Account source account ID. So I'm setting a particular item in the list. Yeah. Source account. Comma. Account square bracket source account ID with debit. With debit amount. Yeah. Next line, dot set item, that's you, and dest account ID. Yeah. Okay. This one. Are we missing something somewhere?
Accounts.
You get it.
Need to go through the house.
You need to go to the accounts. Okay. Yeah. So we're basically producing a new list in a new state. Yeah. Where that state change goes from that immutable list to this immutable list, and that's what we're returning back. So hopefully now, if we go back to the code and use the right bank, which is the immutable bank. Yeah. So this, we're going to. Yeah. And we change that now to the immutable bank. What should we see on the screen? Dots. Is that right? And what have we got is dots. Impressed? How many log statements? None. So this looks amazing. But did we notice anything about the dots? It's slow. So it's not a universal replacement. The question is, why is it so slow? Well, let's fix the slides and we'll find out. How is a regular list implemented? It's an array. Yeah? Indexing through an array is quick. In order to maximize the sharing behavior, they don't use arrays. They use a linked list. A linked list sucks compared to an array for indexing through it, yeah? Because we have to follow references in order to get to the next bit of data, okay? So that's why it's slow, okay? It's not designed as some massive speed up thing. But because it's a linked list, it allows us to do things like this. If the previous list had these 3 nodes in A, B, and C, and you want to add a new node, it builds a new list, obviously, which has a reference to the previous list, which is immutable, it can't change, and it just says at the end of it, there's node D. Okay? So that's really easy. We're sharing the memory. We're not having to do a complete copy every time. Similarly, if we want to remove something, again, yeah, here we've got the situation where we want to remove a particular node B, okay? Now it creates a new node that shares the data array, yeah, which then points to node C. And if there's other things after C, everything will be cool at this point, okay? So it's about optimizing memory. It's not optimizing read performance, okay? So the question is, where would you use this? Well, you kind of think about where did it come from? It came from the Visual Studio team. The Visual Studio team obviously have to support Visual Studio where you are typing away and they need to provide IntelliSense. And that IntelliSense is done by scanning that syntax tree and making guesses, parsing the code. Why it's parsing the code, even with Richard's speed of typing, okay, he's changing things, okay? But what we can't do is lock that data structure while he's doing the analysis, okay? Yeah, so it basically says, I need access to that syntax tree, and I need to be walking through it at the same time someone can be changing it. I don't want to take a copy, because it could be huge, okay? So it's really there for these scenarios where something could take a long time in terms of processing a complex data structure, but at the same time you need someone to be able to change it, okay? And if you have that scenario, that's exactly where immutable collections come in, yeah? It's not a replacement for lists in terms of high-performance scanning through stuff. So, thread safety doesn't have to be complicated. We don't have to work at double check locking, interlock, that kind of level. For lots of stuff we do, we can make use of concurrent data structures, lazy of T, immutable collections, to make our code just as readable as before, but still highly concurrent. Okay? We don't have to sacrifice one or the other. Okay? And that's all about trying to use Microsoft data structures in order to achieve that. Okay, any questions? All good? We have a book. If you want to know more about asynchronous programming, it's there. There is a discount code at the top. Okay? Yeah, so that's the ebook. If you don't like ebooks and you like the paper copy, there is a paper copy. We give away 1 paper copy per talk. And it's really hard to pick someone to give the book to. Okay? Yeah? So we've come up with a mechanism, which we think is reasonably fair.
It is very fair.
Yeah, I'm a bit concerned. So the mechanism is this. I close my eyes and spin on the spot. Okay? And at some point someone shouts, go. And depending on the angle of rotation at that point, I will let go of the grip. If you've got glasses in the front, I'll take them off. What's going to happen to the cameras, I have no idea. Please try
to stand up and protect the cameras. You know.
You'll catch them, yeah? Yeah, okay. So here we go. Now, also, it makes me feel sick. Okay? I do not want to be doing this for 30 seconds, all right? Okay? So that's the plan. Okay, here we go. Okay. Almost the last time, right? Okay. Please, come on.
Go.
That's the first time you've had an animal failure on that.
Is that deliberate? Okay, here we go.
Done.
I'm not done, it's go.
Go.
I want that video.
Improve the video.
Okay, we're done, everybody. Go and have a good lunch. Thank you very much.